Welcome to the session of the Chilean Probability Seminar. We have the pleasure today to have with us Denis Villemonais, who is a professor at the University of Strasbourg, and who's going to talk to us about domination criterion for quasi-compactness of positive operators and applications. Thank you, Denis.
All right, thank you very much for the invitation and the introduction. So first also, I spoke in Chile like a long time ago, but I remember it was a very nice time. So now, of course, it's different. But so just to reassure you, I'll speak about quasi-compactness of positive operators and application to probability theory. So it's mainly about probability theory. Also, we present some recent results on spectral theories that are very useful on, to work on the subject that I was working on at the time. So very quickly, so I first motivate my talk, and so that everyone can understand what it is about. So it's really about the long-term behavior of macroprocesses, and I will speak a little bit, it's necessary, but some notion of spectral theory of positive operators. And I try to explain, do my best to explain why it is useful and how it can be used. And then I explain how we can obtain simply, in some sense, these criteria, these spectral theoretical properties. And I speak about applications. So I present application to some macroprocesses and to non-conservative macroprocesses such as branching processes. And we work that I recently developed with Nicolas that just introduced to me. So. Okay, so my talk is not very long. I mean, it can be long. We always say that, but so do not hesitate to interrupt me. There are some parts that I think are a little bit tricky for probabilist audience, but okay, so normally everything can be understood, so just don't hesitate to stop me. Okay, so first the motivation. So in order to get the motivation, we consider simply a Markov chain, a Markov process that evolves on some measurable state space, E or E plus T, a symmetry point. Okay, so we look at a process, conservative process, or process with absorption at some symmetry point. And the general question that we want to answer is, what is the long-time behavior of the process? Or more precisely, what is the long-time behavior of the law of the process? It is a probability that Xn is in some set when n gets large, or equivalently, what is the behavior of the expectation of f of Xn when n goes to infinity? Or also when there is absorption, and actually it was the main motivation for my study, what is the law of the process on the event of non-absorption? That is, I assume that the process hasn't reached the symmetry point at time n, Xn is not equal to t, and in this case, what's the long-time behavior of the expectation of f of Xn? So of course, the ones among you that know about it recognize that I will be interested into at some point into quasi-stationary distributions, but it's not the topic for now. So of course, there are many studies about these general questions. There are many ways to state it, to state the questions. There are many ways to answer the questions. We can, for instance, in some situation, we can actually compute the law of Xn for each n, and we can have explicit answer to this question, or at least precise estimates. In some cases, we only want to describe it. You can say, okay, it converges to some probability measure, for instance, and if it converges, then maybe it converges in total variation norm or in Wasserstein distance, or at least in law. We can have this type of things. Sometimes it's just to prove the existence, it's already something. Sometimes it's just to prove the uniqueness of a limiting value, so typically of a stationary distribution. So, and when there is a absorption, or I will say also killing, so non-absorption corresponds to survival. So we can also be interested in describing the long-term behavior of the survival probability, the law of Xn. the log xn. So the probability, sorry, that xn has not reached the symmetry point at time n. Okay. So there are many ways to look at this question. There are many ways to answer it, and there are many tools to do it. So we can do, for instance, you can do coupling. You can look at dynamical system. You can look at spectral theory. I will present something about it that are very well known too. As I say, you can do explicit computations and so on. So what is the aim of this talk? The aim of this talk, we could say, okay, so there are many answers. So are there things that can be done that have not been done? Yes, we can, of course. And one of the aim of this talk is to present properties that ensure that the behavior of the process is similar to the one of a process in a finite state space. I will explain what happens in a finite state space and why it's nice. And so we'll see why we want it and what do we want to obtain. And so in order to do it, I will use a spectral theory of positive operators and the notion of quasi-compactness. Okay. No questions? Okay. So the finite state space. Why the finite state space is nice is because the first, it's easy to represent because it's finite, and everything is known in some sense. That is, you know that you can find a partition of the state space with communication classes, and that you can order communication classes. And for instance, in this case, which is a typical conservative case, that is, there is no absorption here. I mean, maybe, but there is no symmetry point, there is no killing. And in this case, for instance, you know that you can describe the evolution of the process with, in long time, with first a function eta 1, that says the probability essentially that the process will go to the left at some point, eta 2, the probability that the process will go to the right, and then when it's in the left or in the right, you know that you will have, I think it's no, I don't know why I put x here, there's no x up. That will be solved, yes. And so in this, and once you know that it's has gone to the left, for instance, then you know that the law of the process will converge to some probability measure, new one, that only charges the left-hand side, and if it goes to the right-hand side, you know that it will converge to some probability distribution that will charge on the right-hand side. And so this is we can systematize this way of describing the law of the process. And in order to do so, to prove this kind of thing, the usual way to do it is to get to define the transition matrix of the process. We take M of ij is equal to the transition probability from I to j for any ij in the state space E. We know that, at least in the conservative case, this defines a finite stochastic matrix. Such that the law of the process at time n is described by the nth iterates of the matrix M. So you just take M to the power n, and it gives you the law of xn. And of course, the answer to questions is just the study of M to the power n as n goes to infinity. This is a way of doing things. Of course, there are other ways of doing it. But then the nice thing is that for finite stochastic matrix, you have the Perron-Frobenius theorem, or at least Perron-Frobenius, or maybe some additional tricks to get there, but it's essentially that. So you have a nice result that describes everything, a spectral theoretical result, actually. And you know that essentially, so I just want you to focus on this part here. So you have convergence of the law. So here you have several things. You have an integer p, which is a period of the system, so because you can have circles. You have, and once you take that into account, you know that it converges to some to see the quantity here. So to sum, as I described before, actually, to some weighted sum of probability measures that can be described as, for the eta left and right eigenfunction, or at least eigenobjects in some sense of the operator M, of the matrix M. Okay. So this is nice, and this is the type of things that we would like to recover, but in the general situation. Can we expect to have this type of behavior in general? Yeah, that's what I say. Okay, and that's when we want to be able to have similar results, similar to the Perron-Frobenius theorem, but in a general state space. So there are many results that provide these. So first, I need to define, to recall or to explain the notion of positive operator. And I hope that it will be clear why it is relevant here. So first, you take E measurable sets. You take the set of bounded function on E. So I take B endowed with a supremum norm. We can use different norm. It's not the point of the talk is not to go into these intricacies, but the infinite norm has some nice properties, let's say. And you take B plus as the set of positive functions. So B is what's called a Banach lattice. That is, it's a Banach space with an order and with a zero as a Banach space. And you can look at all the functions that are just larger than zero. And here our order is simply the natural pointwise order. And from that, you can say that a function f is larger than another function g, for instance, if simply f of x is larger than g of x for all x. Just a positive function, b plus. And then we define the operator p given by the expectation of pf. So I take f, a function, and I build a new function pf, which is bounded to, and which is given simply by the expectation of x of f of x1. Okay, so x is a starting point here. Okay, so this is very usual, of course. And the fact is that may seem nothing, but this operator P is linear, of course, because the expectation is linear, and it is positive because the expectation is positive. Okay, so it means that for any function f, Pf is a positive function. And actually, this type of operators, turns out, have very nice properties. They have been studied a lot, and are still studied a lot by the community in spectral theory. And for instance, you have an older result by Sasser about quasi-positive operator, which is related to quasi-compactness that I present just later, and where Sasser proved that under reasonable conditions, let's say, you have a positive right eigenvector, for instance, for positive operators. So you have a book that is almost complete, almost with all the results known at the time, at least. So it's a large book, Banach lattices and positive operators by Schaffer from 1975. But surprisingly, given just the simplicity of the notion, it does not contain all the results that may be useful to us, and there are new, very simple to state results that have been proved in the late 70s and in the early 80s about compact operators in Banach lattices. So it's typically what happens if P is compact and what happens if P is dominated by a compact operator. I'll come back to that later. So these are very simple things to state, but of course not to prove. And more recent and maybe more useful for my topic book is Positive Operators by Francis Borkinshaw. So I used all these references. Okay, so we have a positive operator, and we'll see what we can say about it. So now So this was simple. Now I need something that is a little bit more involved. I'm sure that many of you are aware of what it is, but I'm also sure that many of you are not. Or to be a bit surprised if it was not the case, let's say. And so I will define what we call a quasi-compact operator. So a quasi-compact operator, there are many ways to define it. So you will find many definitions of a quasi-compact operators. It turns out that they are almost all equivalent. Most of them are equivalent. There are some special definitions that are not, but the most common one referred to the following situation. You say that P is quasi-compact if you can find a finite rank operator. Finite rank operator, think about a matrix. Okay, a finite matrix. It's really it acts like a finite matrix. And we say that P is quasi-compact if P to the power n can be approximated by a finite rank operator to the power n. So it behaves like a matrix to the power n. And it can be approximated geometrically fast compared to the typical size of P power n. What you see the three bars, the three norm is the operator norm, but it gives you just the amplitude of the operator P or of P power n. Okay, so it really says that P to the power n behaves like the iterates of a finite matrix. And that's why it's relevant to a question. It's because well, if P to the power n behave like the iterates of a finite matrix, we have a chance that the underlying Markov chain behave some sense like Markov chain of on a finite state space. Okay. So and Sasser, I speak about it, says that if P is not zero, if P is positive, then there exists a non-zero right eigenfunction to P associated to Rp. So Rp here is a spectral radius of P. It's the largest possible eigenfunction. Actually, it's normally the modulus of the largest possible eigenfunction, but here it's also an eigenfunction. So this is actually a general result, and it's really because of the positiveness of P that you can conclude this. So this is already quite nice because, I mean, you already have it's not free, but if you have quasi-compactness, you have some structure already about your operator. Okay, but it's not enough. It's not enough for us, of course. So what are the consequences for the law of a Markov process? Well, if X is a Markov process, and if P is defined as before as the expectation of f of x1, Pf is the expectation of f of x1, then we can deduce from the quasi-compactness something that is exactly what I wanted. And this is actually a result that is in Yoshida and Kakutani from 1941. So they don't speak about quasi-compactness, but they exactly describe it. And it's quite funny because actually it's from a similar time as a contemporary or almost to the Dublin method, the invention of the Dublin methods, which had a lot of success, but this one a little bit less. And I think it's because proving that P is a quasi-compact operator is usually difficult. But so if P is quasi-compact, this P is quasi-compact, we have exactly what we want. That is, we can find some objects, the eta I, the nu ik, so that the expectation of f of x, pn plus k, where p is some kind of period, again, can define a period in this general setting, it's not too difficult, then it converges indeed to the same thing as before. So we really have the same behavior as in the finite state space case. Okay, so this is nice. So there are two questions now. First, how do I prove that an operator P is quasi-compact? Because now this, I think one reason why this has not been used is because, well, we don't have tools to prove that. Well, we do have now, but I think in 1941 it was much more scarce. And also, do we have something similar for absorbed Markov processes with absorption with a symmetry point? And so that's the first new result that I present to you, original results, is that if X is a Markov process on a state space E plus an absorbing state space T that I consider a symmetry point, that is, I only look at the process before absorption, and I consider the process is just killed and removed from the system when it hit T. So we can define again P T as a new but a very similar operator. So it's a sum Markov operator. It is a positive operator on B. And hence, I can still use quasi-compactness. And actually, what can be proved, so the result will be soon with all the precautions that you can imagine on the archive, but it's not yet on it. But so if you assume, if you're able to prove that P cross is a PT is a quasi-compact, then you can prove that the limiting behavior is similar to the finite state space case. So I didn't present exactly what happens in the finite state space case for sub-Markov process, but Markov process with absorption, but we have something similar. It's just a little bit more complex. So first, on the right here, you still have the same type of limits. It's a weighted sum of probability measures. But here on the left, you have something. So you still have C's exponential renormalization. You have a first, you don't still have, you first have, you have a renormalization factor because you lose, the process lose mass, and RPT in this case is smaller than 1 typically. And so you have to renormalize C's. You have, of course, the indicator function of the fact that the process is still not absorbed when we look at it. And you also have, and this is something that is particular to some Markov process, when the process is reducible, you also have to introduce a polynomial correction. That's the way it works for finite state space processes. And here we do have it for general state space as soon as we're able to prove that PT is quasi-compact. Questions? No? Okay.
Perhaps there is for quasi-compactness, there is a Devlin characterization, but I don't know if the same, but in probabilistic terms, yes?
No, it's not. I think what they, okay, so it's not the same here. But okay, if I go back to C's result, I think, if I remember correctly, that Yoshida and Kakutani do prove that it's equivalent to a very similar, maybe it's equivalent to Dublin in the conservative case, yes.
Yeah.
But it's not true anymore. Actually, the one that interests me more is the case with absorption. And in its case, it's not equivalent to Dublin because Dublin does not give you this type of result. So yeah, but actually in the
it is in the book of Neveu. I remember that it was in the first book of Neveu. There is the Devlin condition for.
Okay. So and there is two. Yeah. So you have two ways of looking at the Devlin condition. There is one that also involves. I don't know, but actually, I think they prove it is equivalent. I think they prove it is equivalent. Yes, you're right. Yeah. In the conservative case, yes. Yeah. Okay. So the new goal now that we understand what type of condition we need to obtain, but it's a formal condition on PT. So how can we prove that P or PT is quasi-compact? This is a new question, okay, that I had once I understood that. And that's when I present to you a domination criterion for proving the quasi-compactness for positive operator. So I explain everything. So first, what is domination? We say that if you're given two positive operators P and Q, we said that P is dominated by Q if for all positive F, PF is smaller than QF. and of course are positive because both are positive. Okay. So this is the type of domination we imagine. For instance, if you think about the process with absorption, so if you get a process on a state space E, and you say, okay, if the process at some point, I will remove the process from E, I will send it to a symmetry point. Then for instance, in this case, the operator defined by the process with absorption is dominated by the positive operator defined by the process without absorption, because you only lose mass when you define the operator with absorption. Okay, so this is an example. So why domination is actually relevant? It's not clear that it has anything to do with quasi-compactness or with compactness. So I just recall, it's not important for the rest of the talk, but it's just for this incredible result, that we say that P is compact, an operator is compact, if it maps bounded subset of B to compact subset of B. And it turns out that I don't really understand why, but it's proved and it's admitted by the community, so I guess it's true. And if you take B an LP space, LP of some measure mu, and from some P smaller than infinity, strictly smaller than infinity, if a positive operator P is dominated by a compact operator, then P is compact. I say this is incredible because it's not true for us. I mean, there's no reason to be true. Okay. So actually, it was Martin Kopp that communicated it to me some years ago, and I found it completely incredible, and that's why I began to look at this spectral type of spectral theory. So you have this result, but which is limited to LP with P strictly smaller than infinity, and at least for the thing that I'm used to, I used to work on L infinity. I find it easier to work with for general Markov processes. But we have another result by Ali Prentice and Burkinshaw in 1981. And they prove that if, in general, B is a Banach lattice, so you just have a Banach lattice with an order, that's all. A little bit more than that, but essentially that's that. For instance, L infinity, it works. And if an operator P is positive and it is dominated by a compact operator, then P to the power 3 is compact. So again, the proof is not that difficult to follow, but I don't have the intuition. If someone among you has the intuition, I'm very much interested. But well, it happens that it is the case, so we can get compactness using domination. Of course, natural question is, does this work with quasi-compactness? Can I obtain, so partial answer, it will be partially yes. Can I obtain quasi-compactness from domination? So it's interesting, for instance, if you're able to prove that a Markov process, process defined by a conservative Markov process is quasi-compact, then this would imply that the killed process is also quasi-compact. It's too good to be true, and it's not true, of course. And to make this work, it cannot be true. It cannot be true because, for instance, it's a little bit long to explain. It cannot be true. It's clear that you can't have this type of domination. And in order to give a statement that has a chance to hold true, I have to introduce the essential spectral radius. Let's do it. So what's the essential spectral radius? So before I say that P is quasi-compact if I can find a finite rank operator, a matrix, such that P to the power n is close to M to the power n. And I said this has to be geometrical approximation. So it was like smaller than alpha to the power n. And here the essential spectral radius is the smallest possible geometric rate at which the approximation is true for some finite rank operator. Okay. So it's a measure of the closeness of the the distance between P and, in some sense, between P and finite rank operator and matrices. It's a way to measure. And actually, it's easy to observe. If you come back to the definition, it's exactly P is quasi-compact if only if the essential spectral radius of P, Rs, is strictly smaller than R. Okay, so this is the characterization that we will use now. And a much sensible statement that has a chance to hold true, at least might be true, it's not clear that it doesn't hold true, is to say that if P is a positive operator smaller than Q, then the essential spectral radius of P is smaller than the essential spectral radius of Q. So this would mean that P is closer to finite rank operators, in some sense. But it is false. It is false. There is a famous example by Depacter and Cherp in 1988. They'll prove it with a relatively simple, but it has to be involved. It has to be involved. You cannot find counter. I think you cannot find counter example in simple situations, because in simple situations, the operators that you get are typically well behaved, and they have to choose something a little bit tricky, but that can be interpreted, but I won't present it, but it can be interpreted in terms of Markov process. So it doesn't work in L2. You cannot prove this statement in L2. So I changed something here. I changed here. Here I had Q, and now I write it as K plus S with K compact. And I change here the essential spectral radius of Q by Rs. And it's just, you have to believe me, but it's just a way to see it, is that if it's equivalent, the statement is equivalent to say that if P is smaller than a compact operator plus S, or a finite rank operator actually, plus S, another operator, then the essential spectral radius of P is smaller than Rs. So see, if we can prove this property, we win in some sense. Okay. So what I managed to prove is that actually this property holds true, but not in the generality, full generality, of course, because it's not true. It's true if you have three conditions. First, you can bound P by a compact operator plus a small operator, in some sense S, with K positive. So this is not actually a restriction. You can always choose K positive because you can always change it to a positive operator with S positive. And this is a restriction because in general, S is not positive. When you have a decomposition of Q as a compact operator plus a small operator, in general, S is not positive. And also, P minus S plus is well defined. So P minus S plus is here the positive part of the operator P minus S. That is, P minus S is an operator that maybe it's a signed operator in some sense. It's not positive, but in some situations that I will explain later, you can find the smallest positive operator larger than P minus S. You have to find situation. This will be true in L infinity, for instance. It will always be true in L infinity when E is countably generated. I mean, the sigma algebra on E is countably generated. Okay. And then in this case, if we have that, so P is smaller than K plus S, then the spectral radius of P is smaller than the spectral radius of S, and this answers the question. Okay. So let's come back to some probability questions. Okay, so I will try. So I had to go through that because it's really the main point of this method. But now I will come back to the Markov case. So you can. I will use what I did, but it will be more familiar to you, I think. Okay. So we'll come back to the case where X is Markov process. And in this case, the operator that we define is actually bounded kernels, bounded kernel. And if the sigma algebra on E is countably generated, then you may know that you can define the positive part of a bounded kernel. It's still a kernel, it's a positive kernel. So you can we have what we want. And so if E is countably generated and P is smaller than Q, the positive part is smaller than Q, then the essential spectral radius of P is smaller than the essential spectral radius of Q. So we do have it. It's true. And in particular, the properties that I mentioned before, we always have that the essential spectral radius of a kill process is smaller than the essential spectral radius of a not kill process. So this is a result that we will try to use to prove things, to derive properties on kill processes, for instance, from properties of the not killed process. So the reason why this works in L infinity and it doesn't work in L2 in general is first because S plus is well defined. As I said, it's because we have a countably generated assumption. It's the first thing that is not true in general, but this is true in L2. Okay, but the thing that is not true in L2 is that, and which is used very importantly in the proof here, is that the norm, operator norm of the positive part of an operator is always smaller in L infinity than the norm of the original operator. And this is useful because for technical reason. But this is the reason why it works here, and it cannot work in general in L2. Okay. So we have this. Let's apply it. So first, just so that you know, it can be used. So there are two, as you saw, there are two results. You have one result that says that, okay, if I have a quasi-compact operator, I have this nice description of the iterates of the law of xn when n goes to infinity. And the other one was about how can we prove that some operator is quasi-compact. So first, the first application is about the quasi-compactness implies nice behavior part, and it's a work that we are finishing fully with Nicolas. Almost done. I think the proofs are finished, but we have to finish the paper just. And okay, so we will consider what we call a weighted branching process. So what's a weighting branching process? So you start here at generation 0. You start with a weight U0 in R plus and a type X in some state space. And depending on the type, you pick U1 a new weight U1, U2, U3, and so on. And you pick new types, Y1, Y2, Y3, and so on. So there may be infinitely many weights and infinitely many types. And what you take is that you build the generation 1 of that by simply taking as the weight of the individual U0, the original weight, times the weight that you just split, U0, U1, and the new type is Y1. And at each time, the law of the weights and the new types of the progeny is determined by the type of the parent. So this gives you an infinitely many weighted individuals. And you do it again and again and again. So you have infinitely many individuals, time infinitely many individuals, and so on. But it's not really a problem because you have weights. So the sum of the weights are typically finite. And if they are not, actually, we cannot do much. And then at the generation 2, for instance, here, you get new, you pick a new weights, U1, 2, U1, that's not U1, 2. What did I do? Tac. Sorry, 2, 3, 4. So 1, 2, 3, 4. And you get, so you pick a new weights, U11, U12, U13, U14, Y11, Y12, and so on. And this gives you the second generation, and the weights are actually given by the product of the weights in all the of the parents and of the individual. And so each time, just some notation. You see that I define W0 as a U0 and W1 as a U0, U1. So it's the weight of individual one. And here it's W12, for instance, is U0, U1, U12. So it's the weight of individual weight 1, 2, and so on. Okay. So more formally, let's get a little bit more formal. So this gives you a way to build a branching process with weights. Importantly, the weights can depend or not on the law of the weights can depend on the type of the parent. Okay, and this is related to when you don't have types, for instance, when the type space is just 1 point. It's related to a famous model that has been studied for people looked at several properties of this model. It's called the Mandelbrot cascades. So maybe it rings a bell. So the law of the weight of the weighted branching process is characterized by the law of the progeny of one individual of type X for any X. So for each X in E, we associate a random vector, U1X, Y1X, and so on, of weights here. This is the weight, and of types. And you do the same thing, and you get the generation N, and you have the weights WE, that depends on the label of each individual. And it's, it's WY here. Okay, and you just look, the point is to look at the weighted sum of all the individuals of one generation. And we want to understand how this evolves. And actually what we obtain, so we obtain more than that, but it's an application. So it's an application of the result we have with Nicolas and the result that I just presented to you. In this case, we want to define two kernels. So first, the mean kernels, that is very similar to the kernels that you obtain when you look at a standard branching process and you want to prove, for instance, the many-to-one formula. So you get QFX is the expectation of the sum of the weights times f of yx. So it's standard. And we also have, we need to use, we introduce a second kernel, which is a kernel. So here I work in L2, but we work in LP for p smaller than 2 in general. But for 2, it's easier to state. So you just put Q2, so it's a second kernel. It's the same thing, but here you see I take the weights to the power 2. Okay, so this also gives me a kernel, and it's just a different one, and it will actually give us the properties that we need. So we assume that Q is quasi-compact with spectral radius of Q larger than 1. This means essentially that we are in a subcritical case. And we assume that the spectral radius of Q to the power 2 is strictly larger than the spectral radius of the Q2. So these kind of properties are a little bit abstract, but you can prove it in practical situation. It just depends on the situation because here the model is too general. Okay. And once you have the quasi-compactness, using the other results, you can understand the behavior, the long-time behavior of the iterates of Q to the power n, and this gives you information on the behavior of the weighted branching process. And if you assume, so this is a more classical assumption, but if you assume in addition that the variance of the sum of ui x g of yi is bounded by g infinity square, then in this case, we can prove that G and F converge in L2 to WF. So this is typically the type of applications that we can get from properties as quasi-compactness. So it's really for Markov processes, for some Markov processes, but it also has application to branching processes, and here for weighted branching processes. Just a remark, we also have, for this type of thing, we also study log L type criteria, and once again, property similar to quasi-compactness is used. Okay, so now I will present an application about the domination criterion. Okay, how can I use in practice the domination criterion to prove that a P is quasi-compact? So the typical case is that if the process X, the law of the process X1, actually, so admits a bounded density with respect to mu for any initial measure. That is, if the law of X1 is bounded by C times mu for some constant C that does not depend on the initial position, then here what you have is that P, the positive operator, is dominated by an operator of rank 1. An operator of rank 1 has a spectral radius, essential spectral radius of 0. So we deduce that the essential spectral radius of P is 0, and hence P is quasi-compact. So if there is a bounded density, then the operator P is quasi-compact, and we can apply all the results that we have. Okay, actually, in the conservative case, I don't think that this is, it may be useful, maybe, but I'm not sure. I think that it has already been studied so much, and there are so many stronger type of properties to study the long-time behavior of Markov process, conservative Markov process, that I don't know if it's useful, but it's easy to understand. But when X is a sub-Markov process, usually things are much more involved, and we don't have a main and 3D for some Markov process. We have many information on it. We have a lot of properties, ways to use compactness, for instance. Of course, there is a book that has been produced in Santiago about quasi-stationary distribution, so you're well aware about it. But we don't have this type of general way of looking at this problem as we have for the conservative case. So in the non-conservative case, well, we still have it. Still true that if X admits a bounded density with respect to some probability measure mu, then the essential spectral radius of P cross is equal to 0. So if in addition we can prove that the mass of the process doesn't decreases faster than exponentially fast, actually, that is, if the spectral radius of P T is strictly bigger than 0, then we deduce that P is quasi-compact. So we have actually a quite practical way to prove that P is quasi-compact, and hence to be able to describe precisely the behavior, the long time, precisely, but still abstract, but we have a way to describe the behavior of the process in the long time. So another application, so here it's still a little bit abstract, but I mean, it can be applied to many situations. Another situation, so more a practical one, for instance, is the one where we consider kinetic stochastic differential equations. So kinetic stochastic differential equation, and here stochastic differential equation with a type of position velocity thing. So here Qt is position and Pt is velocity. So you see that Qt evolves as the derivative of Qt is the velocity, it's Pt. And Pt evolves as a stochastic differential equation, which is typically elliptic. Okay, so the sigma is typically elliptic here. But of course, the full system is not elliptic at all, it's hypoelliptic. And we are interested in the law of the process of the stochastic differential equation, condition not to hit what we call a cylinder. A cylinder is a set which is bounded, position bounded set, and which is of the form d0 position times rd. All the speeds, all the velocities are allowed, but the process is killed when the position exits some set. Okay, so for instance here, so you have the position in abscissa, the position upwards, velocity on the going on the right, and so if you take a process that evolves, so you kill it when it hits the boundary of d0, but you don't have any constraint on the velocity. So, and what you can prove using a note that is an archive, but that we didn't publish with Michel Benaim, Nicolas Champagnat, William Safran on quasi-compactness of very regular, strongly Markov operator, strongly Feller operators, and you combine it with a recent result that we had on quasi-stationary distribution with Nicolas Champagnat and others. We have 5, so we have time at the end. I will tell you the names. But so under weak regularity, but with hippolyticity assumptions, so typically Hörmander conditions on F and sigma, then we can prove that the operator Q is quasi-compact with essential spectral radius 0. And we have, we can prove that Q and F is of the form when n goes to 0 is equivalent to RQ to the power n times some eta Q of X times nu Q of F. Here you don't have a sum because the process is irreducible in some sense. No, in some sense, in the usual sense, and hence you have only one. Here it's a quasi-stationary solution, and you have only one eta Q. Okay, and so here you have 2 papers just to prove that, and we are stuck at the fact that we cannot put constraints on the velocity. We can, if we decide to kill the process when the velocity exceeds some speed, the method doesn't. So how can we go beyond that using the criteria that I just showed you? So take a new set E that contains 0, so that it's you just can stay in E with positive probability. And you define, so it's a subset of the cylinder, and you define PFX as the operator defined by the process, but the process killed when it exits E. Okay, you see here it's killed when it exits E before exiting the cylinder. And so once you have that, you observe that P is smaller than Q because the process is killed before in the definition of P. And hence, according to the domination criterion, we deduce immediately that the essential spectral radius of P is smaller than the essential spectral radius of Q, and hence it is 0. And hence, since E is connected, and actually since, well, it's not connected under these assumptions. The picture that I showed you make it connected, but since it's, but let's say if E, for instance, is convex, then you can deduce that you have the same result. If it is not, it's not a problem. You still have the decomposition that I showed you before when P is quasi-compact, but in this case, P quasi-compact, and hence we have an immediate answer to the questions that we were not able to prove using more standard tools. And I think, yeah, probably I think that if we took more time, like maybe 1 or 2 additional years, maybe, so we have many things to develop. Actually, there are 3 papers that are used to prove the previous criterion. Maybe we would have been able to prove it using different techniques, but really here the point was to show you that actually by going through these rather difficult, I would say, I found it difficult at first, at least, let's say abstract spectral theoretic tools, provide us with a tool that really adds simplicity to prove actual practical results, practical for probabilists, and which is usually more robust. That is, you can take a smaller set, and it will work, but you can also add jumps, you can add change in directions randomly, for instance, in this system, and it will still work because it relies on the fact that the process has a density here, and this is something that is quite robust too when you add jumps. Not degenerate ones, of course, but when you add jumps, redirection, reflections, and so on. And so that's the end of my talk. Thank you.
Any questions? Hi, Denis, how are you? Joaquin here. Nice to see you.
Hi.
And to see your talk. Can you please go back to your result about the quasi-compactness criterion?
Yes.
Domination.
This one.
Okay. Yeah. So in that case, what is S satisfying there?
So S.
Just positive.
Yeah, it has to be positive. Yeah, it has to be positive. It's very important. If it's not positive, it doesn't work. But usually in probability, but not usually, it's not true. It's just often you get this type of decomposition with S positive.
Okay, and then it is K, which is, K needs to be compact. Okay.
Yeah, K is compact, yes, exactly.
I just can't help thinking of, I mean, it also has a kind of a doubling flavor in a way, because you might think that if you have the doubling criterion, well, you will have a measure, a probability measure, which minorizes the
yes,
the semi-group, which would be, which in a way will give you some compactness in the sense that you will, because it will be constant in terms of the.
Yeah.
Vector is a finite dimension. Right. So
yeah, you're right.
And then you have the positive, the other part which you need to be positive. So it really looks like something like Dublin.
Yeah, you're completely right. But actually, with Dublin, you have a better thing than that. You have P equal to K plus S with some. You can write it as with an equality actually.
Okay.
So it's even better with a Dublin. Once you have Dublin, you can check it. But so just to be clear also on the. So you're completely right. So this is especially true, but for conservative Markov process, yes. So as soon as you don't have a conservative Markov process, the Dublin condition is not enough anymore.
Yeah.
And that's when you go into trouble. Actually, it's because of that, and then you have to prove other conditions or things like that to work. But actually, that's what I said at some point. I said I don't think that it is very useful in the conservative case, because I think that in these cases, typically you're able to use Dublin condition. But the Dublin condition is a little bit stronger than that. I don't know if you can directly.
In more general, because your S, you just need to be compact. It doesn't need to be, because in Dublin you have something which is of rank 1, because you take respect to the minorizing measures. Here you have something.
Yes. But it's not that better because it's yes, it's true, but actually if you're in the conservative case, you can first you take out the periodicity. Okay, so you just look at ND, and then you take out the periodicity, and then you look at the different irreducible sub part of your space, and then you get Dublin. So when it's quasi-compact, I think it's the way it works to prove that you do have the Dublin condition. And for conservative process, it's not difficult to see, because as soon as you're in a reducible state space, some sense, you'll see that you have only in the point just before, but here you just only have. I go back to the conservative case. You just have one term here. Actually, eta I will be just eta 1. It will be 1, actually, eta 1. And you will just have a 1 new. And from these, actually, from the result that you get, you can prove the Dublin condition. Because the Dublin condition is equivalent. In some sense, once you reduce the state space correctly, you do have that.
Yeah. Okay. Thank you.
You're welcome.
Are there any other questions? I was wondering, in this case of the weighted, so your applications on weighted branching.
Yes.
So this is like as you say, this cascade story. So usually in the cascade, it's like a phase transition regarding the variance of U or the log U. I could not see exactly how this. Somehow at a point you are converging in L1 and sometimes you are converging just to 0 or somehow.
Yes, exactly. So here typically, so for the cascade thing, you have so you have L log type criteria, for instance, and under L log type criteria, it converges to 1. You have a martingale just for branching processes. You have some kind of Bigins martingale, and then you can prove that the Bigins martingale is uniformly integrable. And that's what we got here. That's what we get here.
In your result, so I could not somehow see exactly in your result where was this hidden, because you always have convergence in L2.
Oh yeah. It's here. It's right here. Here, if you take the cascade, Mandelbrot cascade, So you only have one. Type possible. So actually, the G is just a constant. So you just remove this one. So you get that you assume that the variance of the sum of the UX is bounded here.
I see.
So that's where you get that. And actually, but this is actually the bounded variance clearly gives you you have much finer result in the literature. So they have L log L criteria, and we do not get, of course, because it's more general, but we do not get something that is as precise. We almost get the same results. We almost be able to recover the results that we found for the situation where there is no types. But we still have a condition on QP, and there is something. It's not clear if we can do the same thing in this general setting, but we're not as precise, which is to be expected because. Yeah.
So this should cover the whole L2 regime, but it doesn't go up to the L1 story.
No, so it goes to the L1 if you use the L log L type criteria, but I didn't introduce it because it's a little bit more involved. You have to, but even with the L log L type criteria, you do have to introduce some QP for some P as small as you want, but still strictly bigger than 1. So you don't have anymore the variance of the dispersion in LP, but you don't still have a condition that is not very strong, that we don't have in the literature about Mandelbrot cascade. Yeah. So it goes to L1, but there is some, and I think the method that we use, they are very different from the one in the Mandelbrot cascade community. So I think maybe there is something to understand, but maybe it's not possible. I don't know.
Thank you. Are there any other questions? I don't know if in the Zoom there are questions you can check in the chat. No. I just have one quick question. When you have your quasi-compactness, you showed that you have this convergence to the eigenelements, and this is exponentially fast with your weight alpha.
Yes, in the conservative case.
Yes, but in the sub-conservative case, it's just converging.
Yes, it can be. I mean, it cannot be exponential as soon as a very simple case. Okay, so it's really you don't have to do all this to understand that. It's just you take 2 points, okay, with 2 points plus cemetery point, 3 points. Okay, so you go with rate probability 1/2. You stay on the point. I will build it. I will write it easier. So you take that 1/2, 1/2. And then you have the symmetry point and you take 1/2.
You're not seeing what you're writing.
You're not seeing.
Okay.
It was hidden.
It was hidden before behind the pictures. Okay.
Yeah, now we see.
Okay. Wait, I don't see it anymore. Okay, okay, good. Okay, so you take this thing, so you have 2 points here. Okay. So you stay on the part above with probability 1/2, you go below with probability 1/2, and you stay here with probability 1/2, and you go to the symmetry point with probability 1/2. Okay, so it's not very easy. And if you look at the transition matrix of C's, you can write it as C's way: 1/2, 1/2, 0, 1/2. So it's a stochastic matrix, and you can compute that to the power n. It's a nice exercise for your L3 students, or L2 maybe. I don't know how it works, how fast you are in Chile. And you'll see that here in this case, you will have a term in n that appears. When you take here, you will have something like 1 to power n. You will have 1 to power n, 0, and sometimes that is n time a constant. Okay. So if you want to normalize it, you have to take 1/n times 1/n, 2 power n times that. And what you will get, it's 2 power n. And what you will get is that the distance to the quasi-stationary distribution will always be of order 1/n. So that's why you cannot, with this simple example, you can see it. It's not clear in what I wrote, I just realized, but that you can do the computation and you'll see that it doesn't work. And you have that, and if you have 3 points, you have similar things and so on. So you can't expect to have something exponential in general, but you have it. For instance, there are situations where you can prove that J is 0, and you're in a nice irreducible situation. And in this case, indeed, you have exponential convergence, but it's not range.
Okay, thanks. Are there
Welcome.
questions? If not, we can thank Denis again.
Well, thank you.